Okay, in this section we're going to talk about something called optimization. Essentially what optimization is, we're going to be looking to either maximize or minimize some quantity given some situation where we have some constraints that we have to make sure that we follow. So first of all, you want to read the problem carefully. You want to understand what the unknown is, what you're trying to find, whether it's a maximum or a minimum, and then also what those given quantities are and how those can help you. Two, also, you always want to make sure that you draw a picture. A lot of times can be helpful, especially with coming up with the formulas. And then three, make sure you introduce some notation, and then we're going to use derivatives to solve. So this first question I have is, a farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. Okay, so that's going to be important. No fence along the river. What are the dimensions of the field that has the largest area? So he's got a lot of different options, right? So if he has a river here and he just wants to make a rectangular field, so what he could do is, he could make it a very flat rectangle. He could make it a very tall rectangle that's not very wide. And he's got, it could be almost square. He's got some constraints here. He's only got this much fencing. He's only got 2,400 feet of fencing. So along this river, we're going to have essentially three sides of a rectangle, right? We don't have anything here because he doesn't need to fence this off where that river is. So the question is going to be, how should he make this rectangle so that he has the largest possible area inside this rectangle? And one thing you might want to think of is, the area is not going to be the same. If I did a really skinny rectangle and used up 2,400 feet of fencing, almost all of that going this way, and then just had little sides on it, that area is not going to be the same as if I had maybe a rectangle that looks like this, or one that's even taller than this and maybe a little bit skinnier. Okay, those areas are going to be different. So I'm going to try to find the dimensions, how I should make each side of this rectangle so that we have the largest possible area inside here. So I'm just going to call this X, and it's a rectangle, so those are both going to be X, and I'm going to call this Y. And again, I don't need this part down here because that's where the river's at. Okay, so drawing that picture is going to help. Then we want to think about, what do we want to do? We want to find the dimensions of the field that have the largest area. And so, and when it says largest, that means we're going to try to maximize. Okay, you're either going to be maximizing or minimizing some quantity. We're going to maximize area. And so, at that point in time, you might think, well, how do I find the area of this? The area is simply, in this case, X times Y. Right, to find the area of this rectangle, I would just do essentially base times height, which would be X times Y. I want to maximize this. And the problem is, I'm always going to want to make sure I only have one variable over here on this side. And right now I have two. I have X and Y. So I'm going to, similar to related rates, I'm going to simply try to get rid of one of those variables before I do the derivative part of this. And that's where this comes into play. I've only got 2,400 feet of fencing. Okay, so all of this around the outside here has to equal 2,400 feet. So essentially I'm looking at a perimeter, but you want to be careful because it's not a full perimeter of this rectangle because I do not have this side right here, right? I don't need any fencing right here. So what I have is that 2x plus y needs to equal 2,400. Right? This x plus y, if I add all that together, I've got that 2,400 feet of fencing. And what I'm going to do is I'm going to solve this for y. So I'm going to subtract the 2x, so y would equal 2,400 minus 2x. And then I'm going to take this, since that's what y equals, it's got to be 2,400 minus 2x. I'm going to plug that in for the y over here in our formula that we're trying to maximize. So a lot of times you'll hear this called the constraint formula. So you're going to have a formula that you want to maximize or minimize, and then you're also going to have a constraint formula that you want to manipulate in some way to replace over here. So that's going to take us to the fact that area needs to be x times 2,400 minus 2x. I would distribute the x, so area would be 2400x minus 2x squared. And now once I have a simplified version over here with only one variable, now I'm going to take the derivative. So I'm going to say a prime equals 2400 minus 4x. Now if I'm looking for a maximum or minimum, think about when we found local extrema, a maximum or minimum is going to happen essentially whenever the tangent line is 0, right? Whenever I have a hump or a valley. So what I want to do is I want to take the derivative and then I want to set that equal to 0 and find my critical numbers. So what I could do here is I could factor out a 4, and that would leave me with 600 minus x equals 0. So my critical number would be when x equals 600. I don't need to worry about that 4. And then I just set this equal to 0 and I solve for x and I get 600. What I would want to do at that point in time is go ahead and make, I don't want to do that. Go ahead and make that number line. Put that number 600 on your number line and test just to make sure that this is a maximum, right? I need to make sure it's a maximum. So what I'm trying to do is maximize this. So I'm going to look here at this 4 times 600 minus x. I'm going to pick something left of 600. You do need to slightly be concerned about the domain here. Obviously I can't go below 0 for this is an x value for x, right? Because if you know x is less than 0, then I have no fence there, or I have negative fence there. It doesn't make sense. It could possibly be 0, but we need to strictly kind of be between 0 and essentially 24. Well, yeah. I need to make sure that I don't use up all this fencing, right? So just for this one side of x. So the reason I'm saying this is you need to be careful with what numbers you pick to plug in here. I mean, obviously you could plug in 599 and 601 into this, and that might be the way you want to go. But you could also plug in something like 1. As long as it's to the left of 600, it doesn't really matter. So let's say we plug in 599. We would have a positive 4 times 600 minus 599 would give me a positive 1, which means this would be an increasing quantity here because I'd have positive times positive. And if I plug something into the right of 600 like 601, I would have a positive 4 times 600 minus 601 would be a negative number, which means I'm going to be decreasing over here. And if I go from increasing to decreasing, that means I have a maximum, right? So this is a max, which is what we wanted. That's good. So our maximum happens whenever x is 600. So I know x needs to be 600. And then I can simply find y by going back to this equation where y equals 2400 minus 2 times x. And now I know the x has got to be 600. So y is going to be 2400 minus 1200. And so y would need to be 1200. So the question is, what are the dimensions of the field that has the largest area? It would be when x is 600. So I have 600 on both sides, and then this would need to be 1200. And if I use that amount of fencing in each one of those areas to make this rectangular field, this area would be the biggest of any rectangle I could make, given that 2,400 feet of fencing. Okay, so that's the idea. You know, the actual taking the derivative and doing the test and all that, that's probably going to be the easy part. The hard part might be coming up with, you know, what formula do I need to maximize? What is my constraint formula? How do I plug that in and simplify that part? But actually, you know, when we get towards the end here, hopefully that part was a little bit easier. So in the next video, I'll go through another example of doing an optimization problem.